All right, so in this video we're going to talk about calculating the physical properties of shapes. And what we're doing in this video, or this set of videos, is actually starting to connect some of the ideas that we've already discussed back in the shapes readings with some of the ideas around interactions. And there are really two sort of major things that I want to accomplish in this particular video. The first is to introduce some notational conventions, because that notation is notation you'll encounter pretty frequently, and it's not the most transparent notation, so I want you to be aware of that notation. And then the second the second thing I'd like to accomplish in this video is simply to introduce the idea that you get to make some important choices in framing problems when you're talking about trying to integrate physical properties. So we'll look at some different ways that you could choose to frame a given problem. All right, so far, if you think back to your readings on the shapes, most of the stuff about shapes had to do with the idea that you might want to calculate, say, the area of some domain. So you sort of wrote this: the area of the domain is the integral over the domain dA, or more explicitly, if we write in Cartesian coordinates, dx dy, right? Or if you had a three-dimensional domain, you might want to calculate the volume of the domain. So and conceptually, in both cases, what we're writing here is we're sort of saying there's some, in the case of the two-dimensional case, I've got some domain that's maybe a sort of chunk of stuff, right, that's two-dimensional. It's like a two-dimensional lamina. And what I'm doing is I'm adding up the differential bits of area, these dAs, right, and those dAs are each little squares that are area dx times dy, right? By the same token, if I'm talking about the three-dimensional case, maybe I've got some three-dimensional volume here that is my other domain, right? So that's three-dimensional, as I'm sure that beautiful drawing indicates to you, and I'm thinking about adding up what the volumes are of each little differential chunk inside of this area in order to figure out what the total volume is. Okay? So, and as you recall in the shapes reading, you really went from this fairly abstract notation to some much more specific notation of actually saying, okay, I'm going to integrate from x is equal to some value to some other value, right? Y is equal to some value to some other value, z is equal to some other value. So this actually became a definite integral in order to find the volume of specific domains. So what we're going to do is move in the more abstract direction and actually do a couple of things. The first is to introduce the notation of stopping writing multiple integrals when we're talking about integrating over domains, and instead simply write the integral over the domain of whatever the differential element is. Okay, so when I write this, right, the integral over d of dv, what I actually mean is I am doing the, in this case, three-dimensional integral over the domain D, and I'm adding up what the volumes are. So this notation means the same thing as this. And of course, implicitly in this notation is the idea that D, in this case, is a three-dimensional domain, whereas in this case, I could equally write the integral over this domain D of dA, and implicitly in this case, D is a two-dimensional object. So when you see this sort of single integral with the d under it, it doesn't necessarily mean it is a single integral. It simply means that it's integrating over a single domain that might be one-dimensional, might be two-dimensional, might be three-dimensional. Okay. Also related to that notation is the sort of idea that you don't just calculate volumes, and in fact you started to calculate some other quantities at the end of the readings. For example, you calculated the mass of some object by saying, okay, well, the mass of that object is, if I integrate over the domain, the density times the differential volume, right? So this is what the mass density is in kilograms per meter cubed, right? The differential volume is in units of meters cubed, so kilograms per meter cubed times meters cubed gives me kilograms. When I integrate, I get the total mass, and conceptually, all I'm doing here is thinking about breaking this thing up into little chunks, right? And asking the question, how big is that chunk? What's dV, right? What's that volume? And then what's the mass of that volume? Well, it's the mass per unit volume times the volume. So notationally, you'll often find this written in the more obscure looking form of simply the integral over the domain dm, right, where dm is a differential mass element. Dm is simply this thing. So if I wanted to write that in more explicit detail, I would write the integral over the domain of rho times dv, right? And there's sort of a big kind of general idea here, which has to do with integrating over the domain a differential amount of some physical quantity. And let me give you some examples of what those physical quantities might be. For example, you might be interested in how much thermal energy, or what the internal energy is of a system, right? If you think back to ModSim, you were adding up how much energy was inside of a solar house. Well, if you actually wanted to calculate the energy inside the solar house and the temperature was different at each point inside the solar house, what you would do is integrate over the domain of the solar house du, where du now represents the differential bit of energy contained in each little chunk. And I could write that in more explicit detail as the energy density times dV, right? So now little u is my energy density in joules per meter cubed, right? dV is my volume density of the differential element, which has units of meters cubed. So when I add that up, I'm going to get an energy that's the total energy that's contained in the domain, right? I could also talk about what the number of particles is contained in the domain. Well, the number of particles contained in the domain is simply the integral over the domain of the differential number of particles contained in each little chunk, which I could rewrite as the number of particles per meter cubed times dV, right? So this is number per meter cubed, and this again is a differential element, meters cubed, right? So you'll see this kind of notation of the integral over domain du, or the integral over a domain dn. When you see that, the questions you need to ask are, first of all, what's the domain? What domain are you actually integrating over? And secondly, how do I actually think about this physical quantity in terms of some kind of density, in terms of volumes, and so on? Okay, so that's the first piece that I wanted to point out, is this kind of idea of more abstractly representing integrating over a domain with this type of notation. Okay. Now the second thing that I want to introduce is the idea that you actually have meaningful choices to make in terms of choosing what kind of representation you're going to use for doing a physical calculation of something. And so to get at that, I think I'm going to stop this video here, and then I'll make a second video that actually gets at that idea of choosing the representation that makes the most sense for a given situation.